Okay, hello everyone. Welcome to SMN3043, that is ordinary differential equations for today's presentation. So today, me, Lee Johnson, will represent fellow members to present today's topic. Okay guys, so today's topic we will learn about two equations, that is second order linear homogeneous equation and second order linear non-homogeneous equation. Before I begin our presentation today, let me introduce our fellow members. This is me, as you can see, this is me, Ling Jiasen, and they are fellow members in our group, that is Nurul Afika Nabila binti Amirullah and Aisha binti Muhammad Johaimi. And these are our fellow members from group 2 also, that is Nur Elmi Shuhada binti Ashimi and Nur Fazana binti Muhammad Intani. Okay guys, let us begin our today's topics, that is second order linear homogeneous equation. So based on the given equation, that is p function s, that is d square y over ds square plus q function s times dy ds plus r function s times y equals to g function s. So when it comes to the g function s is equal to 0, that is the right hand side is equal to 0, then we can simply conclude that the equation is homogeneous. That is p function s times d square y over ds square plus q function s over dy ds plus r function s times y equals to 0. Let's look at the example, that is 5y for the second order of differential equation plus 6y of the first order differential equation plus 9y equals to 0. So where can we apply this equation? We can apply this equation in mechanical vibration for the free oscillation and electrical circuit, that is RLC circuit, for the free response. And it is the same equation for the second order linear non-homogeneous equation, but we need to conclude that the equation is not homogeneous when the right hand side, that is the g function s, is not equal to 0. For example, 9 times y of the second order differential equation plus 5 of y for the first order differential equation plus 8y equals to 10. So where can we apply this equation also? We can apply the equation in the mechanical vibration for the forced oscillation and also the electrical circuit, that is the ILC circuit, for the forced response. So guys, here we enter the question and answers for both equation, that is second order linear homogeneous equation and second order linear non-homogeneous equation for the scenario. So let me handle this flow to my friend.
We already know that the equation is homogeneous is when Gx equal to 0. So the equation for homogeneous is a 2 kg object is attached to a spring and damper system. The spring has stiffness K equal to 5 Newton per meter and the damping constant is C equal to 6 Newton second per meter. At T equal to 0, there is no external force acting on the object. The initial displacement is 1 meter above equilibrium and initial velocity is negative 2 meter per second. Find the particular solution that satisfies the initial conditions. For the solution, we already get the given information from the question. M equal to 2, which is the mass, K equal to 5, which is the constant, and Ft equal to 0, which is the force. C equal to 6 and the given initial condition is y0 equal to 1 and y prime 0 equal to negative 2. Then the values from the question we substitute into the standard second order linear differential equation for a spring mass damper system, that is my prime prime plus cy prime plus ky equal to ft. We will get 2y prime prime plus 6y prime plus fy equal to 0. We see that RHS is equal to 0, then the equation is homogeneous. From the equation, we get A equal to 2, B equal to 6 and C equal to 5. Next, find the value of B power of 2 and 4AC. Compare the value and we see that B power of 2 is less than 4AC. Hence, it is complex and we must use the formula yt equal to the e power of alpha t, A cos beta t plus B sin beta t. From the given equation, we completing the square. The coefficient for m power of 2 must be 1, so we have to multiply by 1 over 2. Next, we completing the square by using these steps and we will get m equal to negative 3 over 2 plus 1 over 2i. We compare with equation m equal to alpha plus beta I and we will get the value of alpha, which is negative 3 over 2 and the value for beta is 1 over 2.
Next, we substitute the value of beta into the complex equation above. From our earlier step, we found that beta is equal to 1 over 2. So, the general form of y of t becomes e to the power of negative 3 over 2t multiplied by the bracket of a cos 1 over 2t plus b sin 1 over 2t. After that, from the equation, we are given a condition when t equals 0. So, we move to the next step where y of 0 equals 1. We substitute this into the equation. 1 equals e to the power of negative 3 over 2 times 0 multiplied by a cos 1 over 2 times 0 plus b sin 1 over 2 times 0. Next, we simplify it. Since e to the power of 0 is 1, cos of 0 is 1, and sine of 0 is 0, the equation becomes 1 equals a times 1 plus b times 0. Therefore, a is equals to 1. Now, we have found the value of a. We move on to find the value of b. To do this, we differentiate the function y of t using the product rule. We let u be e to the power of negative 3 over 2t and v be the bracket of cos 1 over 2t plus b sin 1 over 2t. Then we apply the rule u prime v plus uv prime. After getting the derivative, we use the second initial condition from the equations, which is y prime of 0 equals negative 2. We substitute t equals 0 into the expression for y prime of t and solve the equation. After solving, we find that b equals negative 1. Now that we have both values, which are a equals 1 and b equals negative 1, we substitute them back into the general solution. So, the final particular solution is y of t equals e to the power of negative 3 over 2t multiplied by bracket cos 1 over 2t minus sin 1 over 2t.
Okay, for the second order linear non-homogeneous, we are given the equation LQ double prime plus RQ prime plus 1 over CQ equals to ET. When ET is 12, then the equation is non-homogeneous. So the question is, the series circuit consists of a resistor with R equals to 20 ohm, an inductor with L equals to 1H, a capacitor with C equals to 0.02 F, and a 12 volt battery. If the initial charge and current are both 0, find the charge and current at time t. So here we have the given information. We have resistor R equals to 20 ohm, inductor L equals to 1H, capacitor C equals to 0.002 F, voltage or ET equals to 12 V, which is our constant. Our initial charge and initial current is 0. By applying Kirchhoff's law to a series RLC circuit, which gives us a second order differential equation, which is LQ double prime plus RQ prime plus 1 over CQ equals to ET. In this case, we're given values L equals to 1, R equals to 20, and C equals to 0.002, and ET equals to 12 volts. Plugging these in, and we get Q double prime plus 20Q prime plus 500Q plus 12 equals to 12. This is a non-homogeneous equation, which we'll solve in two steps. First the homogeneous solution, then a particular solution. But I will explain until the homogeneous solution. So now let's solve the homogeneous equation first. We rewrite it using the characteristic equation so we can apply it into a quadratic formula. So we change the original equation to r to the power of 2 plus 20r plus 500 equals to 0. Now we apply the equation to a quadratic formula. Now it becomes r equals to in brackets negative b plus minus the square root of b to the power of 2 minus 4ac, close bracket, and over 2. Since the discriminant is negative, this gives us a complex roots, which result in the equation having an imaginary number. Now we substitute the equation. We put in all the numbers. Negative 20 plus minus to the square root of 400 minus 2000, close bracket, to the power of 2. And this simplifies to r equals to negative 20 plus minus to the square root of negative 1600, close bracket, over 2. And finally, we solve the equation one by one, and now we get r equals to negative 10 plus minus 20i. These are complex conjugate roots, meaning the solution will be an oscillating exponential function. So now we change the imaginary number equation to the homogeneous equation, which we get here is QHT equals to exponential to the power of negative 10t, open bracket, a cos 20t plus b sine 20t, close bracket. Now we change the imaginary number equation to the homogeneous equation, which we get here is QHT equals to exponential to the power of negative 10t, open bracket, a cos 20t plus b sine 20t, close bracket. Now we move on to the particular solution.
For the particular solution, since the non-homogeneous term is a constant 12 volt, we assume a constant particular solution is Qp equal to K. Substitute K into the previous equation and then we get 500K equal to 12. Then, after we simplify, we get K equal to 3 over 125. So, we get particular solution is equal to 3 over 125. Next, we need to find general solution. So, the general solution is the sum of the homogeneous and particular solution. So, the general solution is equal to exponent power of negative 10t multiplied with a cos 20t plus b sine 20t, and then plus with 3 over 125. Next, we are given initial charge and initial current equal to 0. That means T equal to 0, then initial charge equal to 0. So substitute to the equation. Then we got the answer for A equal to negative 3 over 125. To find B, we use the first derivative for general solution of Q. So by using product rule, we got the first derivative of Q. Then, given in the equation, initial current is equal to 0. So, substitute T equal to 0 and the first derivative equal to 0. Then, we got the answer for B equal to negative 3 over 250. So, now we can answer the question by substitute A and B into the previous general solution and the first derivative equation. So, the charge at time t is equal to exponent power of negative 10t multiplied with negative 3 over 125 cos 20t minus 3 over 250 sine 20t and plus with 3 over 125. Current at time t is 3 over 5 exponent power of negative 10t sine 20t.
So hello everyone, here we are back again. So based on the Q&A and the explanation, let me make some conclusions. Based on this presentation, we can conclude that the second order linear equation is written as a function s times y of the second order of differential equation plus b function s times y of the first order differential equation plus c function s times y equals to d function s. However, we can conclude that it is homogeneous when right hand side that is d function s is equal to 0. while non-homogeneous when right hand side there is d function s is not equal to 0. So based on the Q&A and the explanation, we can conclude that there are many applications for both linear equations, such as the mechanical vibrations, electrical circuit, and so on. And guys, here we will end today's presentation for the SMN3043 ODE. So thank you for listening. Thank you for lending our ears. I hope you guys like it. Don't forget to subscribe. See you guys. Bye bye.